Hello guys, today we're gonna start with the Boolean algebra. I had at first maybe 60 slides, like I was planning two lectures, maybe finish it, but the last couple of days I did maybe 300 slides, and I divided to 4 parts. So Boolean algebra is gonna take 4 lectures from us. It mainly explains everything about Boolean algebra in details. Like we're gonna take at the beginning what are gates, types of gates, the truth table, logic diagrams. Then we're gonna go to simplification using Boolean identities, and simplification using K-maps. And then we go after that sum of product, product of sum, and how to do some let's say complicated stuff in Boolean algebra, like how to transfer a circuit which has different gates to just NAND and NOR gates. And this is really important, guys. It's not that much required in assembly, but it's good for you guys to use it. And finishing Boolean algebra, we'll finish chapter 1, and then we have chapter 2, which is mainly registers and modes of operation, and then we start the math and programming. So please, if you can, download Massim. Maybe I'll do a small video, 5 minutes, on how to download it after this. Okay, Boolean algebra. So what's Boolean algebra? You also heard about algebra, but Boolean algebra, Boolean, we know 0 and 1, binary numbering system. Boolean algebra is a mathematical system for the manipulation of variables that can have one of two values, which is 0 or 1. And why do we use those? Remember, any program is going to be an equation. A Boolean algebra, any program we can translate it to a Boolean algebra equation. What can we do now? Used to analyze digital gates and circuits, and we're going to see what's digital gates and circuits. We analyze them. Reduce and simplify Boolean expressions. If we can reduce them and simplify them, we gain what? Performance, less memory, and price. And those 3 are really important in computer science: price, memory, and speed. An example of a Boolean equation, we can say A or B and C. Those are the OR and are gates. A, B, C are variables. Another way we can write it is this: A, or, B, and C. And it's not addition and multiplication, it's totally different thing. We can also write it as this is an OR and this is an AND also. By the way, this is 7 in Arabic, 8 in Arabic. So Boolean algebra. Let's see what we mean by that. Base building block of any machine. If I tell you what's the base building block of any machine, electrical device, computer, a CPU, what's the base building block? Remember, we said the base building block of any machine is transistors. What's a transistor? It's a switch, on off. Let's say an on off switch, and we're gonna explain it in detail in a couple of minutes. From transistors, what do we get? Base building block transistors, small, on off, which is 0, 1, true, false. You can consider it as you want. From transistors we can make gates. A gate is an AND, an OR. We have mainly 6 gates we're gonna cover. There's 7. Some people consider the gate, I'm gonna explain it later, as an extra gate, but I don't put it as a gate. Some people do that also. It's similar, we can find out with another gate. From gates, what can we get? From gates we can get integrated circuit. Integrated circuit, for example, a CPU, an FPGA, a chip, a microchip. An integrated circuit is a microchip that does a special task or application. So base building block is transistors. We can think of a transistor as a switch, light switch, on, off. If this is closed, it passes current, or it's 1. If it's open, it's 0, value of binary. And if you go to the history of computers, what did they use before transistors? They used vacuum tubes, light bulbs, to build computers. But the problem with those, they get damaged really quick. They introduce lots of heat, so the transistor replaced them. I think they came out in 1947, the first transistors. What are transistors? Semiconductors used to amplify and regulate current or voltage flow, and acts as a switch or gate for electronic signal. Switch or gate for so it amplifies. The first major reason they did transistor was amplifying the signal. Let's say voice, you amplify it, and the way it does it, remember we said it's a switch. If I play with it in the range, I don't totally close it and I don't totally open it. It's in the middle here, that where the amplifying happens. It's good to know exactly how do we build transistors, N, P, N, and different positive, negative, positive. It's good to know it. It won't take maybe 5-10 minutes if you put YouTube how transistors are made. You'll get it, but I'm not going to explain it here. You don't need to know that. And from transistors, what can we do? Gates. This is a transistor, emitter, base, and collector. If I pass current from here, it allows for a large current to flow. If a small current flows here, it allows for a, so if this is closed, think of it, it passes a 1. If it's open, it's 0. Here's some types of transistors. We can see the size. Like this is really small, this is even smaller, those get bigger and bigger and bigger. Now a really good thing to know, transistors, you all know Moore's law. The density of transistors on a chip doubles every 12 to 18 months. Meaning if I have as this block as a chip and I have 500 transistors on it, next year I can put 1,000 transistors. In other words, the size of a transistor shrinks to half every year, let's say. IBM, just let me show you, I read it a week ago. Let's see if I can find it. What was it? IBM has a 3 billion transistor. Here, silicon nanosheets, IBM. Here, this one. A new computer chip can fit 30 billion transistors on your fingertip. IBM new computer chips can fit 30 billion transistors on a fingertip. Think of that. So next year, how much can we have? 60 billion. And by adding transistors, what do we gain? We add more computation power and more storage, depending on what we're using it on. And this is thin field effect transistors. This is what they came out with, and this is going to be really, really helpful. But the problem, this is a good research topic, is how long is Moore's law going to stand? Like next year I'm going to have, this year we have 30 billion, next year 60 billion, the year after 120 billion, the year after 240 billion. Am I going to be able to put 240? Am I gonna be able to put 480 billion transistors? No, this is gonna stop, and when it stops we're gonna have a problem. How are we gonna gain more speed and more computation power? This is a nice research topic. Who's ever thinking of doing it? So transistors, from transistors what do we get? We get gates, and we said we have basically 6 types of gates. They're not I think you need to know the truth table, the logic diagram, memorize it really good for each gate. Is an idealized or physical device implementing a Boolean function, implementing either an AND, an OR, an AND, an OR, a NOT, an XOR. Those are not gates, those are integrated circuits. This is an integrated circuit, and this is an integrated circuit. And if you look, where did we have a picture? Oh, it was the 30 billion. This is what a wafer that has. This is how we do any chip, any gates, any transistors, using a wafer of silicon. A wafer of silicon, and those are, if you see those small parts, are the chips that we make, and each wafer we can cut it into several pieces to create chips or microchips or integrated circuits. So integrated is a collection of gates that implements a special task. Okay, Boolean, we can describe the behavior of any circuit by, so any circuit, integrated circuit, a CPU, an FPGA, any chip, a microchip, an airplane chip, those remote control airships, the microwave chip, all those are considered circuits. So we can describe the behavior of each of those circuits in 3 ways. Mainly a Boolean expression, an equation, A or B. This is an equation. This is expressing it of a circuit in a Boolean equation or Boolean expression called. Another way is using logic diagrams, having this here. I have A or B and C. The logic diagram for this here, what do I have? This is the logic diagram for an AND gate, a 2 input AND gate with 1 output, and this is an OR. We can see there's a curve here and an OR. And why did I do it? Why did I put the AND first? Why didn't I say A or B here and then did the AND has a higher precedences than the OR. Some people argue you don't need that in Boolean algebra, but I think it makes a big difference. There's really like half of them say it's not important. You can use, they can say you can use like parentheses, like I can put those and that's it, but we can do that also in C++. So this is an AND gate, this is an OR gate. The output of this AND is ORed with what? With A. So Boolean expression, logic diagrams, and truth table. This is the truth table of this. What I mean by truth table is, let's put this should be F. A truth table describes the behavior of this circuit. I have 3 inputs, so each one takes a value of 0 or 1, so I have 2 to the power 3 possibilities, which means I have 8 possible values for all those 3. I can have A 0 0 0. This is 1. 0 0 1. This is another option. So I have from 0 to 7, which is actually 8 options, including the 0. 0 to 7. 0, 1, 2, 3, 4. That's how I do them. This is converted to binary. In any instant of time, I have only one of those. So what does that mean? I can have what's A as 1, So I can have A as 1 and C and B are zeros. This will give me an output of 1. So my output here will be 1. This what this means. I can have it 1 1 0, which is this one, and I can have still an output of 1. This is a truth table describing the behavior of this logic diagram, describing this in logic diagram. This is I'm describing the Boolean expression as an equation. 3 ways to describe Boolean algebra, and we're gonna learn how to flip between those. But let's go here to gates. Boolean expressions are created by performing operation on Boolean variables. And actually the CPU, what does it do? It's limited. It does arithmetic and logic operation. We said logic operations, or bitwise operations they call them, which is like those performing operation on Boolean variables. Boolean operation gates include, we have how many gates? 1 2 3 4 5 6. 6 gates. Some people say we have 7 gates. They consider the XNOR, which is the opposite of XOR. It's a new gate. It came after, but first we had those 6 gates, then this came. So there's lots of people that still consider those. I can still implement anything from those. We are adding a NOT just for the XOR. So how do I go back to this? We had what? Transistors, which are switches. We get gates, which are those 6 gates. From those 6 gates I can implement. This is what builds your computer. Any electrical device are built from only those 6 gates. You don't need anything more. A NOT, an inverter, 0 to 1, 1 to 0, an OR, an AND, an OR, XOR, and an AND. And we're gonna take, if you saw the next slide, the truth table, Boolean expression, and logic diagram for each one of those. How do I describe logic? In 3 ways, or Boolean algebra. A Boolean operator can be completely described using a truth table, the Boolean operators, and known as a Boolean product or operator is the Boolean sum. This is the Boolean product, and they think of it as product, multiplication, or as sum. So let's see here. Here what do I have? I have an AND gate. This is an AND gate, and this is putting a dot here. Okay, this describes it in a Boolean expression. This describes the logic diagram of it, X and Y, 0 and 1, whatever I had. This is the truth table, meaning if I have 0 0, the output is what? 0. If I have 0 and 1, the output is 0. 1 and 0, the output is 0. 1 and 1, I have 1. If X is 1, Y is 1, the output is 1 of an AND gate. But look, that's why they call it the product. Look at those 3 is thinking 0 multiplied by 0 is 0, 0 multiplied by 1 is 0, 1 multiplied by 0 is 0. Here we have the OR gate, X, Y, X or Y. This is the Boolean expression, this is the logic diagram, and this is the truth table. And we said it's like the sum. 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. This is the truth table. And please guys, you need to know those. You need them. I don't think you need to memorize them, but try to understand it. Like those 2 are easy. This is a product, this is a sum. And you only have what? X and Y, 2 inputs. So I have 2 to the power 2 possible outputs or variable or options. So it's 4 options. The NOT gate has only 1 input, 1 output, is an inverter. I input a 0, it gives me out a 1. I input a 1, it gives me a 0. It has only two possible values. This is the truth table, this is the Boolean expression, and this is the logic diagram. So those are three gates, mainly the basic three gates. Then we have the NAND gate. NAND gate is what? AND with a NOT. AND with a NOT. Gate, we can think of it. AND with a NOT. This is an AND gate. Or two NOTs with an OR. And we're gonna explain this. This is actually De Morgan's law. Remember, De Morgan's law. We split the complement. This is the NOT. Split it and change the sign. So here I have X NAND Y. And what's the truth table for the NAND? It's the opposite of what? AND. Because think of an AND and I put a NOT on it. So here I put a NOT. It's going to give me what? 0 is going to be a 1. 0 is going to be a 1. 0 is going to be a 1. 1 is going to be a 0. This is an AND. And we can describe it as, think of it this way. This is the Boolean expression exactly. One complement, sorry, let's put it here. Oh, it doesn't show the X and Y with the inverter. And how did I do it in an OR? De Morgan's law says we can distribute the complements, meaning X or Y. Change the sign, change it and to an OR. If it was an OR, I change it to an AND. Those two are equal. Those two are equal. So now we have the NOR. The NOR is what? An OR with a NOT. An OR is an OR, or all of it complemented. This is the Boolean expression. This is the logic diagram, and this is the truth table. And if you see, it's going to be what? The inverse of this. 1 0 0 1. So this, using De Morgan's, which we're going to take in a minute, is going to be what? Distribute the complement and change the sign. I have addition is going to be AND Y. That's why it has it this way, because I have the complements before the actual operation. Here I do the AND has a higher. And this is the XOR, and this, we can't say we distribute one of those, but this is actually what's XOR. XOR is when I have the same input, 0 and 0 gives me 0, 1 and 1 same input, it gives me 0. When I have different inputs, it gives me 1. This is the easiest way, and this is, we're gonna use it in binary division. When we do long division, usually we subtract. In binary, we do the XOR operation. So the XOR, whenever I have the same input, it's 0, different inputs is 1. This is the truth table. This is the logic diagram where I have a curve and this, and this is the Boolean expression. Please guys, this is really important to memorize, to know Boolean algebra. Everything builds on this. It's really important to know it. I don't think it's that hard. So let's see this. Find the logic diagram and truth table for the following expression. Logic diagram, I have a Boolean expression, and I need to find the other two. Remember, we can describe any circuit or Boolean in algebra, or diagram, or microchip or chip, in 3 different ways: Boolean expression, logic diagram, and truth table. And here they gave me the Boolean expression, and they told us to find the logic diagram and truth table. So how do I find the logic diagram? Let's look. What do I have here? And what do I have here? But remember, presidencies, what's first? This is okay. I want to see how they drew it, but okay, how I do it, I forgot. But here, I don't know if I took the presidency into account. Here I have the parentheses, so I'm gonna do the x and z, this is z, as two inputs. I'm gonna have them to a what? What's this operation? And OR gate is gonna be, and excuse my, I'm trying to make it the best as I can. This is an OR, and usually I write an OR here, especially in your exam. So if you're, but what do I have on an X? I have a NOT. So I'll invert whatever I have here. I have a NOT gate here. And if we go back to this slide, where did it go? Here. Here's the NOT, and here's the OR. I'm going to use this, and I'm going to put a NOT on the X because of the complement. Now what do I do? Here, what do I have between those? Those are ANDed, the X and Y and ANDed, and between the X and Y and those I have, and so this is gonna, but usually we don't put that, the dot, the AND, this, and now I have another dot, another AND, so it's gonna be X NOT or Z. This is mainly what's this. So I have the OR. Now what I'm gonna do, I'm gonna AND it. This is the AND. This one, I'm gonna AND it with what? The result of what? An AND gate also. Is an AND, where I have X and Y. X and Y ANDed together will give me the result here of X and Y. Then I AND this. Here I have the AND gate, which is actually this one, let's say, and OR with those. That's why we said the presidency sometimes is not important. If we did this first, it's not going to make a big difference. But let's see, I want to show you mainly this. Okay, what the Boolean algebra, okay, simulator. A, oh, I forgot the A. Which one? Simple solver logic. Academy, this has a nice one. There's other ones that has really good ones. But where's Academy? Academy. Here we can draw circuits, and this is what I usually see. Here's the inputs. We have 1, 2, 3, 4, 5, 6. See why I told you the X node is not that much used. So this is on. This is just to run the circuit. What am I gonna have? Okay, no, I don't need this node. I don't want this node for now. I want, what was my equation? We had the OR. We needed an OR. Add node. Here's an OR. Where I had, why did it go down? And we had an AND, and we had another AND. Why is those like that? Come on, how do they move? Why is there? I think I needed the input one. Come on, what's wrong? Okay, let's go try. I don't know what's going on with it today. Let's see. Oh, as they appear. Simulators. What is wrong? Simulators, they gave me the same one. Where are they? This is just equations, okay. Chrome, go down just for a minute. Why? Oh, they're not giving it to me today. Okay, now it's working. Mainly because we needed to add an input node. Okay. And we have an OR, X and Y. And then let's add another input. And another input, which is, think of them as the variables. And let's do it real quick. Come on, move. No, this is not moving. Okay, now it's saying it's good. And add a node. And we need another input. And we can simulate the output of the. So we had an OR, and one of those OR was okay, knotted. I think the X was knotted. But how can we have a wire, right? In this case, what am I going to do here? Okay, connected it. And this is X naught or Y. And this is X and Y. And we had them ANDed together. And I can say this. So this is my, you can put here the value 0, 1, whatever you want, on, off, simulate it and see what it gives you. But here I don't have the, I don't allow it to do what JavaScript. I can allow it, but that's for more security, guys. It's better to do that. So we draw this x and z, x or z, x not or z, and x and y. So this was describing the logic using logic diagrams. Oh, why did it go to? Now we have another way by describing the logic was using what? Truth tables. So how can we describe it using a truth table? Remember we had the 0, 1, here 3 inputs. Here's the truth table. How many inputs do I have? X, Y, and Z. The x naught is not another input, it's considered, so I have 2 to the power 3, which is 8, so I have from 0 to 7. So here's what's gonna happen. Let's get my pen. This is 0, this is 1, 2, 3, 4, 5, 6. I'm missing one here. 1, 2, 3, 5, 6, 7. Okay, I think I'm missing. So what will this be? 0, 0, 0. What will my output be if I had it 0, 0, 0? Here's what we're gonna do. This is, let's say, function f. This is the result of the output. If I had 0 and 0, go to this truth table, or think of it as product. This is gonna give me a 0. X naught, meaning 1. This is 0, x is 0, x naught is 1. 1 or 0 is 1. So now I have 0 and 1 is gonna give me 0 multiplication. This is the way how I build the truth table. I put all possible inputs. This is going to be all possible inputs from 0 to 7, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, which is 2, 0, 1, 1, which is 3, 1, 0, 0, meaning what? 4. And what do I mean by 0, 1, 2, 3, 4? This is the binary values. This is 1, 2, and 4. From what? 2 to the power 0, 2 to the power 1, 2 to the power 2. And this is find the Boolean expression. Okay, we did the logic diagram here, and we find the results here. This is going to be, as we told you, 0. This, for example, x and y, this is going to be 0, x naught is going to be 1, or is going to be 0. Now x and y is 0, x naught is 1, or with 1 and 0. Because I have an and, this is going to be a 0. Now here what do I have? X and y, this is 0, because this is going to make a 0, it's going to make the whole equation 0, and this is 0. Here I'll have x and y, 1 and 1, x naught is 0, or z is 0, so this is going to give me a 0. This is the only case where I'll have an output of 1. This will be, the last one will be 1. Now here's another example. Find the Boolean expression and the truth table for the following circuit. Boolean expression and truth table. First go get the Boolean expression, and then find the truth table. So here what do I have? Let's start with it from here. I have an OR. So an OR is what? Where should we write it? Here. Or what do I have? I have B not B. Oops. I'm using, there was a paper under this. I was wondering why is it. So I have a B, and it's not it. Not meaning what is wrong with the mouse? It's B not from this, OR with C, and we can do an addition, OR with C. Then what do I have? We can put parentheses here. I have this, which is A, and this is an AND gate. A dot B, and then what do I have? Those can be what? Those here I'm supposed to have an or between them. Then I'll do this is what? An and with a not. And here's I have A, here I started with the A not. This is going here. And then I have that NAND it with what? With B. And how do I do an AND? An AND is going to be a dot B, and both of them complement. So this is an AND, this is this gate, this basically, and this. So then what do I do? Those are XORed, and XOR is an addition with a circle, XORed with what? With, let's start with here, A and B, A dot B, and then I have B not ORed with C, and this is for both of those are ORed together. This is basically this, and this is this, and they're ORed together. So this is the logic diagram, this is the Boolean expression. Now I can get the truth table, and here we have how many inputs? A, B, and C. So I have 2 to the power 3. I have 8 possible different inputs from 0 to 7. 0, 0, 0, and this is gonna be the 7, the last one, 1, 1, 1, presenting what? 7 in binary. And we can build the truth table. When building the truth table, I have a long equation like this. First, go get the A naught. What's A naught? It's the invert of this. So I have 4 ones here, 4 zeros, 4 ones. 4 ones are 4 zeros. Just invert it. 0 is 1, 0 is 1. Now what do? Do the NAND. NAND what? AND B, and then do the complement. I AND it with B. What do I AND? The A naught with B. So this is gonna give me what? 0 and 0 is 0. 0 and 1 is 0 and 1 is 0. 0 and 1 is 0. 1 and 1 is 1. 1 and 1 is 1. 0 and 0 is 0. The ones in red, zeros. So this is the possible outputs. Now what do? Now I find the NOT. So to find the NAND, which is the inverse of this, so 0, 1, 1, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1. Now what do? I find the A and B. A ANDed with B. Here's the A and B. 0 and 0 is 0. 0 and 1 is 0. 1 and 1 is 1. So this is basically doing the AND between those, which is this. Now what am I gonna do? I'm gonna do this. B naught ORed with C. Do I have the B naught? No. So I'll find the B naught, which is the inverse of this, and it gives me this, and I OR it with what? With the C. This C ORed with the B naught. 0 or 1 is gonna give me a 1. Remember, it's addition. 1 or 1 is gonna give me a 1. 0 or 0 is gonna give me a 0, and I find that all of those. So I got this and I got this. So now I do this, which is AB, this one, ORed with this, because I've got those with this. I'll get all this, I'll XOR it with what? With this, which I have it here. So let's see the next step. A not B, which is this one, with this one, and they have an or between them. I didn't put the parentheses, I didn't want to take a space because the picture was going so big. So I have 0 or 1 is 1, 0 or 1 is 1, 0 or 0 is 0. So I get this. So now I have this. I XOR it with what? With this, the one I have here. So this and this will give me the final. 1 XORed with 1. Remember we said the XOR, if they have the same input, is 0 different input, 1. 0 same input, different input, that's 1. Those are all what? Same input as this, same as this. So 0, same inputs are 0, different. This is my final circuit. Saying if I have my A as 0, 0, 0, A, B, C, the result of that gate, when I connect those gates together, is going to be a 0. When I have 0, 1, 1, when I have A0, B1, C1, I'm going to get, passing throughout those all gates, I'm going to get at the end my result as 1. And this is basically describing the circuit or chip or integrated circuit, however you want to think about it. But remember, we have 3 ways to describe circuits. First was a Boolean expression, logic diagram, which is the drawing of the gates, and the truth table. Now find the Boolean expression. We took the first example was what? I gave you a Boolean expression and told you to give me the other 2. This was the first example, and we did that. Then I gave you a logic diagram. I told you give me the truth table and the Boolean expression. Now, and this is the hardest, giving you a truth table and telling you give me the Boolean expression and logic diagram. Find the Boolean expression logic diagram for the following truth table. And this is, we're gonna explain it more in detail, but think of sum of product. Saying sum of product, I'm gonna put the standard of sum of product. And here's what this mean doing it in sum of product. I go look at the ones, where I have ones as my output. This is the output, this is my output. So I look for the ones, those, and I represent them as sum of product. So this is gonna be what? 0 meaning A naught, and sum of products. This is products, and this is sum of products. Think of it that way. So A naught and it will C, sum of products, and D, which is 0, 1, 1. And I'm gonna look at the other one is with this one where I have 1, 0, 1, which is A, and C now is 0, so I'll do the complement, and D is 1, so it's going to be this. Or also, I put it here, so I'm supposed to put it here, but I'm going to put it down here. With the, I only have 3 ones, so I have 3 equations, and I add them all together. 3 products, and I sum them together. That's why they sum of products. I have 1, 1, 1, which means A, C, D, and I close it. So this is my equation, and here's how we write it. This representing this, A naught, C, and D. I add it to A, C naught, and D, sum of products, plus what? I only look for the ones wherever I have a 1. The 0 is not important. If I had 4 ones, I'm gonna have another equation. If I had here as a 1, I'm gonna have plus what? Plus A naught, C naught, D naught. If I had one, but this is here one. this, don't worry about this. There's the product of sum, but we take the zeros, it's not the ones. So here today we covered the basics of Boolean algebra. Remember, Boolean algebra, Boolean is binary, 0 and 1. Where do I go to 0 and 1? Where do I get 0 and 1 from? From switches or transistors, 0 and 1 on off. From transistors, what do we get? We get gates. We have 6 types of gates, and, or, which is a product and sum. We have the NOT, which is the inverter. From an AND, I can get an AND, an OR from an OR, and we have the XOR, 6 gates. From those 6 gates, I can build any integrated circuit. An integrated circuit is a collection of gates that implement a special task, a special application. It can be a CPU, a calculator, a clock, a microwave. All those are considered to be as integrated circuits. We took how to describe circuits in 3 main things: a Boolean expression, equation, logic diagrams, and truth table. So this summarizes what we took in this lecture. Please, if you have any questions, leave it in the comment section. Please guys, try to download Masson. I'll see now if I can put a video on. The problem, I don't have Windows, but if you go to the Masson page, you can download it from there, or I'll bring the link in there. I'll add it either on this video or the next video. I'll keep adding it in every video below in the comment section or the description section. Thank you guys.